Today you're going to learn how to actually use the Heston model in the real world and apply this under the risk neutral measure to option prices. So here we're going to go through the math and we're going to explain the characteristic function for the semi-analytical solution. And then we're going to actually implement this in Python. And then we're going to take that analytical solution, semi-analytical solution, because we actually need to perform numeric integration on this complex space. And the way we're actually going to calibrate our model then is we're going to have all the parameters in the Heston model that we're interested in. And what we're going to do is we're going to use an objective function that minimizes the square differences between our Heston estimated price with a certain parameter set versus the market prices. So let's get into it. So here we're going to be using my Jupyter notebook, but I have lent on a lot of resources to put this together. So we're going to be using aspects of that as we go along. So first things first, Heston stochastic volatility under the real world probability measures. You'll be very used to seeing these equations by now, and if you've watched my past videos. Now, the thing that we need to do is we actually need to translate this from the real world measure to the risk neutral probability measure. And the reason we want to do this, we want to estimate the parameters used in the risk neutral world. So we're going to use the option prices to find the risk neutral parameters. So what we have to do to actually translate from our real world measure to our risk neutral probability measure Q is use the Gersonow's theorem. Now here on Stack Exchange, someone called Kevin has gone through this solution for us using Gersonow's theorem. So if you would like a detailed approach on how to do that, please take a look at the link in the description. So once we've applied those translations, we can actually get our SDE under the risk neutral pricing framework. So under the Q probability measure. So here are our SDEs. You'll note here that we now have this new parameter called lambda, which is the variance risk premia. So here you can see our parameters in terms of the real world parameters to the risk neutral parameters. And these will pop up within our characteristic function. So just a reminder for all the terms that are in here. Remember, kappa is the mean reversion rate. We've got theta, which is the long run variance, V0, which is our initial variance, and then sigma, which is the volatility of variance, or the volatility of volatility. So here, don't forget that we've got the correlation parameter, which is the correlation between the two Wiener processes, between the returns distribution and the variance process. So let's import some dependencies. So we've got OS, we've got NumPy, Pandas, Matplotlib, SciPy integrate, we're taking the quad because we need to perform numerical integration. We've got SciPy optimize, we're importing minimize, date time. Now we are going to be using end of day historical information. So this is an API service, so we can get a whole bunch of call options for the S&P500 index really easily into Python. I'll show you that later. And we're also going to be using this module here, Nelson Siegel Svensson, which is how we can actually just calibrate the yield curve and get the zero coupon rates. So here I've drawn on a number of academic papers and online resources, and all the links are in the description below, so feel free to take a look at that. Now, the standard arbitrage arguments that we arrive at from Garman's partial differential equation here under the Heston model is that we can actually build a solution that looks a lot like the Black-Scholes model. So here we have the stock price times by this probability 1, which is the delta of a European call option. And here we've got minus the discounted strike with this probability 2, which is just like the conditional risk neutral probability that the asset price will be greater than K at maturity. So both probabilities 1 and 2 also satisfy that PDE with the characteristic functions phi1 and phi2. So these are known in terms of P1 and P2 and are defined in terms of an inverse Fourier transform. So if you manipulate the PDE in terms of the log of S, so this X prices, this is how you arrive at this characteristic function. So what Heston did is he assumed that the two characteristic functions had this form. Now there's a reason why he assumed that, but we won't go into that into this video. So if you go through and you solve the PDE, then you're going to come up with the analytical solution for these parameters. So we've got C and D in terms of all the parameters below here, and we've got even parameters that they depend on. Now, for any help for going through that entire process, there are quite a few papers here. I recommend this Heston stochastic volatility model implementation, calibration, and some extensions by Sergey Milkelov and Erlich Nogel. This is really comprehensive and it's very easy to go through the steps. What I will say now is that as soon as you want to try and simplify it in terms of one integral, so remember we have S times P1 minus K, the discounted strike times by P2, as soon as you want to actually simplify that formula into one integral, that's where I think that a lot of the online resources have mixed up signs and made small mistakes. So it's really hard to find what is the true one integral under European pricing. So let's take step by step through here and let's try and filter out the correct signs for this characteristic equation. So what we're trying to do is we're just trying to add this Fourier integral into our European call equation now. And what we can do is we can obviously just take the S and discounted strike out to the left-hand side, and we're left with this Fourier integral on the right-hand side. Now we've still got our two characteristic equations, and you can see phi 1 and phi 2. So what we want is we want one equation in terms of phi, and we want to be able to change these parameters so they're not dependent on the two states. So the correct form for phi is here. And how did we get here? Well, essentially, here there is no longer changes with regards to B1 and B2 constants or U1 and U2 constants. Now, why is that between the two characteristic functions? Well, essentially, let's explain that when you rearrange the solution and then you work out that B1 and B2 and U1 and U2 are no longer featured. So if you remember that this characteristic component is broken down in C plus D times V plus the complex number I, phi x, well then remember that x is just ln s. So what we can actually do is we can work out that e to the power of ln s to the power of I phi is actually just S I phi. So what does that mean? Well, that means that we can actually take that down outside of our integral. So now if we just consider C, we have this R phi I tau. Now we can immediately take that down as its own exponent. Now for this component here, you can see that we have negative 2 ln. So we have e to the power of an ln. So obviously what we can do is we can multiply through this front term in the exponent, so that's a divided by sigma squared. So we get minus 2a over sigma squared, and we put that up to the exponent of the ln. Once you've got it in this form, then you can just bring this whole term down. So we actually have that exponent 1 that we spoke about multiplied by this entire term here. And of course what you're left with is the exponent, which was this bj minus rho sigma phi I plus d tau multiplied by the alpha tau and sigma. So in all the solutions when these two integrals are separated into P1 and P2, these Fourier integrals, essentially you've got two solutions for dj and gj in terms of B1 and B2 and U1 and U2. And what we want to do is we want to create the one Fourier transform so that they're all the same under the same equation. So this will make it easier in terms of actually implementing and numerically solving this integral. So how can we reconcile the difference here? Well, essentially all of this is taken into account in the offset of this phi characteristic function. So our first characteristic function becomes an offset by the complex number 1 compared to just the characteristic function with phi. Now, how can this be? So here I've got the math for understanding the changes in that bj term, and I've tried to put it and then the uj term respectively in terms of d, and I've tried to lay that out as succinctly as I can. If you'd like me further explanations, just leave comments in the section below and I'll try and explain better there. So the first thing we're going to do is we're actually just going to implement this characteristic function in Python with all our parameter terms. So here we're going to calculate these parameters here, which are part of the characteristic function, d, g, a, and b, and we're going to use them then to calculate exponent 1, and then term 2, and then exponent 3. So let's get into the Python. So here you can see that I've got phi and then all my terms here. So S0, V0, kappa, theta, sigma, rho, lambda, tau, and r. We're calculating the constants a and b. I'm combining this term called RASP, which is just because it shows up a lot. So that's rho sigma times phi times the complex number, which is just ij in Python. D is very simple. All we're doing is the square root, which is just rho sigma times phi times complex number minus B, all squared, plus phi times complex number, plus phi squared times by sigma squared. Now, G is just represented by B minus ras pi plus D, all over B minus ras pi minus D. And then calculating the characteristic function, we just do it by components. Again, that was just exponent 1, term 2, and exponent 2. Okay, now that we actually have the characteristic function, what we can do is we can actually define the integrand as a function. Now you have to do this if you're going to use a known numerical solver like the likes of SciPy. So again, for the integrand here, we have all of our parameters, and I'm actually placing this all in terms of the args, which gets passed through to the Heston characteristic function. So here I'm just got the exponential of r times tau times by the first characteristic function, which remember is just the offset by the complex number, and then minus k times the Heston characteristic function with just phi. In the denominator we have the complex number times by phi times by k to the power of I phi. Now, if you weren't going to use a package like SciPy, then we can actually perform this numerical integration ourselves, and the easiest and simplest one is probably one that you learnt in high school mathematics, which is using rectangular integration. So this is where we're going to use the midpoint to calculate the height of the rectangle, and we're going to multiply it by the width over this integration space. So for rectangular integration, we got Heston underscore price underscore rec. We got all our parameters, and again, I'm passing through args to our Heston characteristic function. I'm doing the same thing in terms of the numerator and denominator as before when we defined the integrand, but this time I'm going to step through the integral with n steps. So I'm taking 10,000 steps. I'm going all the way to 100, not infinity. 100 is plenty enough for the types of integrals we're doing here. And I'm starting off with a 0 price. The width of my steps is just going to be Umax, so 100 divided by n steps. So here we're just calculating the midpoint that we're actually going to calculate phi at by taking the steps and then going through each time step. And then once we've got the midpoint, we place that into our characteristic function, and we offset for the first term by minus the complex number, and then in the second term just passing phi. So here each time we multiply by the width times by the integral, and what we get is we're adding this to the area to that price every time. Once we've got that, I can return just the real component, and we have p divided by pi, because that's what the integral was divided by, and then I just need to calculate this half of s minus discounted strike. So that's returning the Heston price using rectangular integration. Using the SciPy, and then we can actually use that integrand function that we defined. I just have my args. I'm going to use SciPy integrate quad function, and I'm going to return the real part, which gives me the real integral component and the error. So I've got quad, which takes my function, which is the integrand, and then I have, what am I starting with? Well, I'm going from 0 all the way to 100, and I'm using my arguments as all of these. They get passed through to my integrand function. And then in the same way, I take that real integral component, I divide by pi, and then add a half of s minus the discounted strike back to get my Heston price. So let's test that. Well, essentially here, we've just got parameters to test, initial asset price and all the other parameters in the Heston model. We just use Heston price using the SciPy integrand function quad, and we can work out what our price is. So that's an easy implementation. Now let's get into the crux of this video, where we actually go through and get real options data so we can actually calibrate this model. So first thing we need to do is get risk-free rate data from the US daily treasury yield curves. Now you can get that from this website here. And essentially what you do is you can just click here and then look for the table for the daily rates, and we have that in terms of the 1 month all the way to the 10-year tenures. So once we've got that information, what we can do is we can get that in terms of the maturities, which is the time in terms of years, and then the yields, which was just the information in the table. Don't forget to get that as a percentage, so divide by 100. Then I'm going to use something to actually bootstrap my curve. Well, we're going to actually use a parametric approach here, which is the Nelson-Siegel-Svensson model, which is just an ordinary least squares approach. So we're going to fit our curve using calibrate NSS OLS, and we're just going to pass our yield of maturities and yields in there. So then we have our curve fit for this model, and you can see all the parameters that have been parameterized with our real world data there. We need this because then when we have options at all these different prices, we can just easily calculate what the risk-free rate is at all those time horizons. Now, for the end of day historical data API. Now, I have recently made a collaboration with end of day historical data, and essentially what they are is that they're an easy to use financial software API that are across a large name of stock exchange for all different types of ETFs, indices, option prices, real-time data, intraday data, etc. Now, I have a link in my description which allows you guys to sign up here. Pricing is actually pretty good. So the all-in-one package, which I recommend, is the $80 one here. But again, you can actually sign up for free and then you'll get 20 API calls per day, which is nothing, but at least to test out whether you're going to be using this API or not. So again, you can get a whole range of financial data, but I think one of the best things is being able to call it for options data, which is very, very easy. So as I mentioned, my link through to that is in the description below, but check it out if you're interested in getting a cheap financial API. So here I've got my API key, and I've just stored it as in the environmental variables, and then I associate my end of day historical data module with the API key. So just initializing that class, and then here I'm getting a response, which is a function called getStockOptions. And I'm just going to get the S&P500 index option prices. Because I haven't defined any parameters or dates, essentially I'm just going to get the latest bid-ask information, last traded, last volume, and all that latest information for prices offered right now in the market. Once I've got that response, essentially that end of day historical class forms that into a dictionary in Python. It's taken the JSON and formed a dictionary for me, and now I can just index that dictionary for what I want. Now you can take a look at the code here, and essentially what I'm doing is I want all the strikes, I want all the expiration dates. I want to set up another dictionary where I then define the strikes and the price for all the call options. So once we've got that, what I want to determine is that which strikes across all these maturities have actually been traded. So if I don't have products offered in the far 10 years, then I don't really want to see them. So I've done this all strikes, and I'm just comparing the sets of all the strikes at all the expiration dates. I'm getting the common intersection, and then I can see that I have 22 common strikes. So once I've done that, I can set up a price and maturities list, and then I can work through all these market prices in my dictionary and calculate the maturities in terms of years, and then I can calculate the price from all the strike prices if they're in that common strike list. Once I've got my price array, I work out that I've got 41 by 22, so 22 strikes and 41 maturities. From there, I actually want to decrease that horizon a little bit. So I had time all the way out to 4 years, but yeah, the volume there necessarily wasn't necessarily trading or all that liquid, so maybe not that representative of the space that I'm interested in calibrating my model. So I've just shown you how you can subsection a data frame here. So we've taken this surface as the data frame with our price array, indexes the maturities, and columns are the strikes. And then I've just said, I only want the index if it's greater than 0.04 years, but less than 1. And then also if the strike's greater than 3,000 or less than 5,000. And then I've just printed out my data frame here so you can see what those prices, market prices in terms of index points look like here for the options. So now what I want to do is I want to take this data frame and I just want to flatten it, so that we actually get a price for each one of these corresponding maturities and strike. Then once you've done that, what you're going to do is you're going to create another column called the rate, which is where we take the maturity and we're going to apply the curve fitted by our yield curve. So we're just going to find out what the risk-free rate is using our parameterized model from NSS to actually fit the risk-free rate into this pandas data frame. Now, the objective function we're going to use from this is from this paper here. Now, link in the description. Essentially, we're going to minimize the squared errors, but with a weight term and a penalty factor. So first off, we're just going to call this penalty factor 0 today, but again, you could come up with whatever you want. And for the weights, this is very crucial to how you actually calibrate this model. For example, you might want to put less weight on less traded volume at later tenures or at wider strikes that have less volume traded. Whereas we're not going to consider that today. All of the strikes and tenures that we've chosen on those index options are quite liquid, and essentially I'm going to weight them all the same. So it's just going to be 1 divided by n times m, which is just for every market price. So here I'm just taking the market price. I'm going to calculate the Heston price with the parameters, with a set of parameters that we have, and then I'm going to square it, and we're going to take the sum over all those squared errors. Here, my optimization, my objective function becomes the parameters that minimize this squared error over the entire set. And as long as I have parameters, this U parameter, that's compact and in a range that a solution exists, I'm all good to go ahead with the objective function. How do you actually implement this? Well, we're going to use SciPy minimize. So first thing we're going to do, we need to define what the actual starting index price is, and that's just from our JSON response that we had before, and it's the dictionary of the last trade price. Then I've got my rates, which is just from my vol surface long, which is the rate, and that's to numpy float. Here I've got my strikes. Again, we're just going to take that from our pandas data frame. We're going to take tau, which are the maturities from our pandas data frame, and we're going to take the market prices from our pandas data frame. Those are all floats. We then have parameters. So the parameters we want to optimize are V0, kappa, theta, sigma, rho, and lambda. And here for SciPy, you need your initial guess. So I've defined that as x0, and then we have a lower and upper bound. So here at the lower bound, I've got 0.001 and with an upper bound of 0.1, and essentially you can make this whatever you think is reasonable. Remember that rho correlation can only go between -1 and 1, and suitable values of lambda, I wasn't too sure, but taking a look at a range of academic papers, of which I've included here on the website, I think -1 to 1 was fairly indicative of that risk premium for volatility. So once we've got that, I'm just going to create a list comprehension of my start values and my bounds, and I'm going to define my squared error term. So my squared error term, this is my objective function. I have x, which is just all the parameters. So I have a list comprehension each time for params in param in x. I just unpack the variables, and then I pass them in to my Heston price rectangular function. I'm just taking the price minus that calculated price squared divided by the length of that price series. I'm just using numpy sum to calculate the sum of the error. If you wanted to add the penalization term, here's where you would do it. I decided just to comment that out in the end, and then you would return error plus penalty. So to actually execute this, you just call SciPy optimize minimize, which I just had as minimize there. We've got our function, we've got the starting values. I have the tolerance, so how much I want to change each of these individual variables by, what method I'm using, and essentially you're going to be limited here by actually having to include bounds, so only a couple of the methods. You might have to go take a look at the documentations. And here I'm defining a number of max iterations so it doesn't take too long. As we run the result then, essentially we get our values back in this X array. And here I can just define those parameters by unpacking them with list comprehension. Once I have that, what I want to do is I want to calculate these estimated options, and then I actually want to visualize them on a surface plot. So here I can just use Heston price rectangular integration scheme using those variables, and then I'm just going to add that to my vol surface long pandas data frame that I had before. Now the vol surface long I can then print out, and now I can see I've got my maturity, strike, price, rate, and now my Heston price, and you can see that the Heston prices are actually pretty close. So we do have some error, but again we've calibrated on 364 rows, different prices, different maturities up to 1 year across different strikes. So that's obviously pretty good there. So let's actually visualize those market prices versus the Heston prices. We're going to be using Plotly here. So Plotly, I've got a mesh for my actual prices, for my market prices, and then I've got the scatter, 3D scatter points for my Heston prices. And here I'd find that it's just useful to visualize that in a plot. But essentially we've got the market prices here as that blue mesh, and then my calibrated Heston prices are the red dots. And you can see it's, you know, there is some error in terms of point values on particular strikes and timelines, but we've pretty much got it bang on. So essentially that's how you calibrate the Heston model for option prices, European option prices on the index. So hopefully you got a lot of value out of this. To actually calibrate a Heston model for American options, we need to come up with a finite difference scheme. Now, we haven't gone through that here on the YouTube channel, so we're actually going to take a step back and start from beginning of finite difference schemes and then go through to more complex applications of the likes where we would actually be calibrating a Heston model to American prices. So hopefully you can use this code and you can play around with it. Also, I really encourage you to go through the math step by step. There are a lot of different resources online which may or may not be true, with just changes and differences in signs between those different analytical, semi-analytical solutions. I think the complication has come about when you actually combine both of those integrals into the one, and then you have to define your parameters correctly. So I think that's where some of the signs sometimes get mixed up, but I encourage you to just step through the math line by line on your own. Take a look at these papers for help. Now, if you did stick all the way to the end, I really appreciate you guys sticking around. I really want to try and build my Patreon community. So I've just started up. We have a Discord channel, and right now we have 50 members where people are trying to participate in active discussion on everything quant finance. So it's only $1 to sign up for the actual Discord channel. If you'd like access to my Jupyter notebooks, it's $6 Australian per month. But essentially, I'm really trying to get as many people as we can to get across to this quant community. So if you're one of the people that have stuck around to the end of the video, please subscribe to the channel and join the Discord channel to be part of a like-minded quant community.